All right, so this third unit covers two chapters. It covers chapter 5, which deals with circular motion, and it covers chapter 6, which deals with energy and work. And circular motion is a very important set of physics ideas that we're going to carry forward and use a lot in Physics 30. So today we're defining what's called uniform circular motion, and we'll talk more about this in a bit, but uniform circular motion cannot be confused with uniform motion. It's totally different. Just a reminder, uniform motion is motion in a straight line at a constant speed. Uniform motion, which we've already studied, can also be thought of as zero acceleration, but you cannot do that with uniform circular motion. There's something called a circular acceleration involved here. We're going to be defining some terms, frequency and period, as they relate to physics and uniform circular motion, and then solving some very introductory problems dealing with uniform circular motion. So, for example, we're just going to, as a warm-up, consider an object moving in a circle with a constant speed. This can be anything. This can be a rock lodged in a tire on your bicycle as you're riding down the road at a constant speed. This could be a point, or it could be you on a ride at the Edmonton exhibition, or a child on a ride, a merry-go-round that's going around and around. The question is, explain why even though the speed is constant, the object is accelerating. So I'd like everybody to give that some thought and type in what you would write for an answer here. The object is moving in a circle with a constant speed. Why, however, even though the speed doesn't change, why is the object accelerating? Which is a very deceptive question. It is because of the direction, Mackenzie. And let's go back and let's talk about what the word acceleration means. Acceleration which is a vector, means velocity, which is a vector, is changing. That's the definition of acceleration. Evan, what you said there is something that we could go with, but analyzing circular motion in 2 dimensions, which is where you're heading, is something we don't want to do in introductory physics in high school. There is a way to explain it mathematically the way you've described it, but I'm just going to go with maybe a simpler approach, which is to say acceleration means that velocity, boy, I'm hurting with my grammar skills this morning. Acceleration means velocity is changing. And since velocity is a vector, any change in velocity means there's acceleration. So what does changing velocity mean? Changing velocity could mean speeding up. It could mean slowing down. Or it could mean, which is the case here, changing direction. Now, I don't want to go too far down the rabbit hole here and spend a lot of time with what I'm about to say, so I will just say it and we'll leave it at that. If you can imagine, you're in the smoothest riding vehicle that has ever been manufactured. It is 100% soundproof. You can't feel any motion from the outside. And you're traveling down the highway at 100 kilometers per hour, and your eyes are closed. So you're not even aware, Rolls-Royce Phantom, sure. You're not even aware of what's going on outside. When are you aware that you're in a car that's moving? There's 3 situations. One, when the car accelerates, right? So let's say that you're sitting in the passenger seat, you've put your coffee from Tim Hortons God forbid, on the dash of the Rolls-Royce Phantom. Your eyes are closed and you're at a red light and the driver hits the gas suddenly. Well, you experience something, and so does your coffee. You apparently feel as though you're kind of pushed towards the back of the vehicle. You're not. What's happening is you're being left behind as the vehicle moves forward. But when the vehicle speeds up, you notice it. Imagine now you're fast asleep or just drifting and you're traveling down the highway at 100 kilometers per hour. You don't know that you're in a vehicle that's moving. But if a deer runs out on the highway and the driver hits the brakes, you will experience something. You will also experience something when the driver swerves or changes direction. We all know that when you're in a vehicle that turns to the left sharply and rapidly, you feel pushed outside to the right. So the reason is that the direction of the object's velocity is changing. What is the direction of the acceleration of the object? This is an interesting question. And it's a very difficult one for a student to come up with the answer to, but you have an object which is, let's just say at this point in time, it's moving in this direction. And I don't think it would help you to write this down. Don't write it down. The object is moving in that direction. Now, we've already established it's accelerating, but there must be no net force forward. In other words, everybody, there has to be an exact equal but opposite net force backwards. So if the object is moving left to right, that means that there has to be an equal force backwards as there is forwards. The explanation for that is very simple. If the forward force was greater, then it would be speeding up. If the backward force were greater, it would be slowing down. So where's the net force? The only explanation is the net force is some force inward. And this force has to be exactly perpendicular. This is the net force. It has to be exactly perpendicular, and now I'm going to get rid of these and put in, this is going to be a confusing diagram, I'm going to put in a velocity vector and the net force. Let's even say there are no other forces. Why does the net force have to be perpendicular to the velocity? Because if the net force were even a little bit in that direction, then part of it would be in the same direction as the velocity and the object would speed up. Why can the net force not even be angled back a little bit? Because if it is, then part of that net force would be slowing the object down. And that means that the direction of the net force is perpendicular to the direction of the motion. F net, well, acceleration, which is the direction of the net force, is perpendicular to the velocity. This is a confusing thing because I know when you hear the word acceleration, you think speeding up. And then earlier in the course, I said, well, it could mean slowing down, but now I'm telling you it could mean changing direction. What is the direction of the net force that causes that? It's the same. It's perpendicular to the velocity. Okay, so what does that mean? What does it mean to say that it's perpendicular to the velocity? Well, we'll get to the specifics of what the actual direction is in a second. Okay, so this is where we put it all together. A ball on a string is rotating clockwise at a constant speed, and the diagram below shows a snapshot in time. So this ball is following this path. Okay. On the diagram, draw the velocity vector. So I'm just going to start with that. Which way should I draw a vector on the ball that shows the direction of the velocity of the ball? Is the ball at this point in time moving this way? Well, I hope you understand that it's not, because it's attached to a string. The string is preventing it from moving further away from the center. Is the velocity of the ball at this instant in time this way? Well, no. I mean, I suppose it could be if I were reeling the string in, but it's a piece of string. It's not getting longer and it's not getting shorter. So which way is the ball moving here? And this is a difficult thing. In class, I would ask people to point with their hands which way it's moving. But here, I want you to try to put into words the direction that it's moving at this point in time. Or if you're up for it, draw in pencil on your diagram a vector showing the direction you believe it's moving at that instant in time. Turn your camera on and show me. This is one of the most difficult concepts in physics. Okay, so first of all, the first part of what Andrea is saying is, wouldn't it potentially change? I think you mean velocity. And the answer is yes, the velocity is changing every instant. The velocity is changing all of the time because it's not going in a straight line. So I think what your first question is saying is, wouldn't the direction depend on where the ball is? This diagram, I want you to note, Andrea and everybody, is not showing it at rest. It's showing a snapshot in time. So the answer is yes. The direction that I draw the velocity when the ball is here will be different than the direction that I draw the velocity of the ball when it is here, and it will be different than the direction that I draw the velocity of the ball when it is here. See, this is a very difficult question, and before I was taught this and it was explained to me, I had a huge misconception. So I'm going to back off of the question that we're being asked here right now. And the question is this: I'm twirling this around, twirling it, twirling it, twirling it, and at this instant in time, what happens is the string breaks. So I'm going to have to do it here. So at this instant in time, the string breaks. The question is, and I got this wrong the first time it was asked of me, where does the ball go when the string breaks? And I know what most people will say. And most people will be wrong. Except for Liam. Liam's got it right. It's going to move perpendicular to the string. I thought that if I were standing here, that I would get conked in the head with the ball. And I won't. If I'm standing here, I will get conked in the head with the ball. Because at that instant, and now we can answer the question, at that instant, the direction that the ball is moving is actually this way, perpendicular to the string. At that instant, and as Andrea pointed out, that direction is going to change an instant later. And Evan's got it as well, perpendicular to the radius. So we can label that in, that's the velocity vector. Now, what direction is the acceleration? So I'm going to be drawing on this diagram three different kinds of things: a velocity vector, an acceleration vector, and a net force vector. So what direction is it accelerating? Well, imagine, everybody, that it's accelerating, and I'll use a different color. Don't write this down. Imagine that it's accelerating in that direction. That cannot be right, because if it were accelerating in that direction, it would be speeding up, wouldn't it? If the acceleration is in the same direction as the motion, it's going to be speeding up. But it has to move at a constant speed. Right? It has to move at a constant speed. So the acceleration can't be that way. Maybe the acceleration is this way. Well, if the acceleration is that way, the object would be slowing down. Maybe the acceleration is this way. I mean, it's not. I don't know why I picked that particular direction. But if the acceleration is that way, I hope that you can see there is a component to that acceleration that would speed the object up. That's exactly where we're going to go with this eventually, Evan. Can you think of this like a planet's gravitational pull towards the sun? The acceleration is going to be inward. Get rid of this stuff first. Because if you think of, say, a planet in orbit around the sun, like Evan is doing, there's no string, right? But the fact of the matter is, there is a pull towards the center. So this is the acceleration vector. And since the acceleration is towards the center, that must mean that the net force is towards the center. Now again, we're drawing three different types of vectors here. You can't even compare them. We've got acceleration, velocity, and now we have force. It's like comparing the taste of an apple to the color of the sky to the smell of barbecue sauce. They're just three different things. You can't even start to compare them. Now, in terms of the string question, the reason why the force is towards the center, and you'll have to actually do this maybe to convince yourself, but if you attach something to a string and swing it around, you are always pulling it towards the center. That's what the string is doing. And if this were the sun and a planet around it, that force would be gravitational. And we're going to end up doing that analysis later. Okay, so when an object is moving with this type of motion, we call this uniform circular motion. So from now on, you need to know that uniform circular motion means moving at a constant speed in a straight line. Now, how is this different than uniform motion? This is absolutely crucial to the big picture that I talk about. When I say students who are successful see the big picture. I don't know if you remember, but in my classroom I have those sheets of paper pinned up on the upper bulletin boards that talk about physics principles. This, by the way, is physics principle 0. Uniform motion, if you look at your formula sheet, is physics principle 0. Look at your formula sheet. I'll put it up here. Under physics principles, the very first principle says uniform motion. And what I've taught you is that what that means is constant velocity. So uniform motion is motion with a constant velocity. But velocity includes direction and speed. So what that means, and part of me says we shouldn't have to write this, but I think we better. Constant speed in a straight line. But this leads to something very important. How can I put this? When we first studied uniform motion, it was all just about objects moving at a constant speed in a straight line. And I seem to make a really big deal about this straight line thing. Well, now I can tie it all together with the last unit and say that what this means is the acceleration is 0. Constant velocity means 0 acceleration. And in terms of this last unit that we just finished, if the acceleration is 0, guess what the net force is? It's 0. And for uniform motion, which is what we studied since the beginning of the course, it could be that there are lots of different forces acting on the object, but they all balance. And if they all balance, when you add up those forces, you get 0. Uniform circular motion is constant speed in a circular path. And what that means is changing velocity. And what that means, if the velocity is changing, you have to really stop and think every time you see what I'm about to write to make sure you understand what it truly means. What that means is that the acceleration for uniform circular motion is not equal to 0. What does not equal to 0 mean? It means there is an acceleration. The acceleration has some value to it. And what that means as well is that the net force is also not equal to 0. And I will tell you right now, that net force that I just wrote down that's not equal to 0, that's the circular force towards the center. That's that force that we drew in the diagram. Now, if you look on your formula sheet at physics principle number 2, it says uniform circular motion. And what I would like everybody to add to that for physics principle number 2 is the following. I would like you to add, for this one, that it is accelerated motion. So, I've had an argument with Albert Ed about this. Number 1 says accelerated motion. But number 2 is also accelerated motion. We'll come back to this again and again in this course and in Physics 30. It's non-linear accelerated motion. Perfect. It's circular accelerated motion. And Andrea, what I was just going to do is say that the difference between this that's highlighted, and I want to make sure that you get this because I don't have a whole lot of room here, and neither do you on your formula sheet. What I was just about to write is that physics principle number 1 is linear accelerated motion. Andrea chose to say, could we call physics principle number 2 nonlinear? Yes, I would prefer, though, if you're going to do that, Andrea, let's call it circular, because there's other types of nonlinear paths that objects could take. But no, in retrospect, I think nonlinear is a really, really good thing to say about physics principle number 2. And the bigger picture here, everybody, is that 1 and 2 are both accelerated motion. Physics principles 1 and 2, let's see if I can move stuff around here. Yep. Physics principles 1 and 2 are both acceleration not equal to 0, whereas physics principle 0 is acceleration equal to 0. And you might think I'm just talking here to give you more stuff to memorize and think about. No, I'm talking here because, again, the physics principles lead you to how to solve a problem. That's what we were doing in the last week or so with all the free body diagram questions. You can't figure out what formula to use until you build it from the physics principles. Okay, so that's question 5. Question 6, not question 6. And now I have some things to tell you. This type of motion, we don't use the word circular. We're going to stop using the word circular. We're going to use the word centripetal. Not to be confused with centrifugal, which is something different that we might talk about later. So instead of saying uniform circular motion, we say centripetal motion. The net force that's responsible for this motion is called a centripetal force. And the acceleration is called a centripetal acceleration. So when I go back and look at my diagram, I could write, I don't want you to, I could write F net centripetal. And the reason I don't really want to do that is F net in this situation is always centripetal. We don't put that. And I could put A centripetal, and I could put V centripetal. But we don't. We generally don't do that. There will be the odd case with V where we do, and A, but we'll get back to that, and we'll include those subscripts when we need to. Okay. The word centripetal actually means center seeking. I don't know if it's Latin or Greek or, well, it's got to be Latin. It means center seeking. So the force is towards the center. The object is trying to get to the center, but it never can because of its perpendicular motion. And basically, just think of the centripetal force as being any force or combination of forces which results in the circular motion of the object. So no matter how many forces there are acting on an object, as I'm driving around a circular racetrack in my truck, no matter how many different forces there are acting, the end result is I travel in a circle, so there's a centripetal force. And that centripetal force, we're leading up to something which is very important about it, is going to be the net force. So later on, you're going to probably start to think that centripetal force is some special force. Like there are forces of friction. There are gravitational forces. There are electric forces and magnetic forces. A centripetal force is not a separate type of force. It might be an applied force, or it might be a force of friction. In the case that Evan said, if you look at the planet Earth revolving in a circular orbit around the sun, there is a centripetal force on Earth, and the centripetal force is the force of gravity. It turns out when I drive my truck around a circular curve, the centripetal force is the force of friction. So the centripetal force can be anything, but the most important aspect is it's the net force. In terms of free body diagrams, if you add all the forces together, you will get the centripetal force because the object actually moves in a circle. So now we're going to be doing some calculations. You will need your calculator out. I guess we got to do definitions first. 3 definitions: cycle, period, and frequency. Cycle is one complete orbit. Or one complete revolution. So if a tire spins 4 times, it's gone through 4 cycles. The period, capital T, it's important that it's capital, is the time for one cycle. So it's the time in seconds it takes for the object to go around once. The frequency is how many cycles per second. And I'll give you the units here. The units for period are seconds, and the units for frequency are called hertz. And all a hertz is a cycle per second. So if I told you that we had a frequency of 100 hertz, something spinning around 100 times per second. All right, now we can continue with the warm-up. L bug clings to the side of a bicycle tire that's making 8 complete revolutions in 4 seconds. And the distance from the center of rotation of the bug to where the bug is 22 centimeters. By the way, we probably want to use meters here, so you can write 0.22 meters. First question, what's Ms. Bug's period of revolution? How long does it take for her to go around once? Well, let's see, it went around, what did we say here? 8 revolutions in 4 seconds. So what we could do is set up a ratio here. 8 revolutions is 4 seconds. The time for 1 revolution is called the period, which is capital T, and we can cross multiply here. Now, some of you may have been able to figure this out without using a ratio, but that's only because the numbers they divide evenly. When you cross multiply and divide here, you get 0.5 seconds. This is capital T. What is the frequency of revolution? So how many revolutions does she make in 1 second? So for this second question, what we can do is we can put 8 revolutions over 4 seconds equals x revolutions, which is the frequency in 1 second, and we cross multiply and solve. We're trying to find out how many revolutions per second there are. Well, if it's 8 revolutions in 4 seconds, then the frequency is 2 revs per second, which is 2 hertz. And the most important aspect now, what is the mathematical relationship between the period and frequency? They are reciprocals of each other. Just take your calculator and take 1 divided by 0.5 and see what you get. You get 2. If I reciprocate the period, which is 0.5 seconds, I get 2 revs per second. Go ahead and take your calculator and take the reciprocal of the frequency. What do you get? 0.5. They're reciprocals of each other. And by the way, this formula is on your formula sheet. I'll show you where it is when we need it. What is the centripetal speed? Okay, so how fast is this bug moving? Well, we can start off by saying speed equals distance over time. But if we take the period to be the time, which is the time for 1 revolution, then the top is the distance that she travels in 1 revolution, which is called the circumference. So if we take the circumference divided by the time, we'll get the speed. Well, circumference, you can look at your formula sheet actually. You actually have a mathematics section of your formula sheet. I think it's on the same side as the constants, but I could be wrong. But it's a section called trigonometry and geometry, and for a circle, you're given the circumference is 2 pi r. So we can take 2 times pi times the radius, and that's going to give us the circumference. Which is 1.38 meters approximately. We can take 1.38 meters and divide by 0.5 seconds, which I believe was the time for 1 revolution. and we get 2.76 seconds. Can you confirm that we get 2.76? Okay, good. Sorry, meters per second. All right, the next question, 10. What's an equation that we could use? Geez, do we have to think this out every time? No, what we can say is that the centripetal speed of an object will always be 2 pi r over the period. Always. Because 2 pi r is the circumference, and the period is the time it takes to move one circumference. So now if you go back to your formula sheet, that formula is there. It's a kinematics formula. 2 pi r over t, capital T. By the way, if you look at your formula sheet and go to the section on waves, you will see your formula relating period and frequency. It's also used for wave motion, which we will learn about when we come back after Christmas break. Like, get back in the classroom. We won't be learning about waves for a very long time. All right, now it's time to do some examples. And we only have about 23 minutes left in class, so you're going to have some homework, but I think I've set the foundation for everything here. The foundation is the following. The period is the time per rev. The frequency is the reciprocal of the period, which is the revs per second. And the speed can be found by taking 2 pi r over t. That's what we're dealing with. And I can't believe that that image is slowing down my computer that much. So I'm going to get rid of it. So those are the three things that we know. So on a hard drive, a traditional, actual mechanical hard drive, not a not a solid state drive, but a drive that actually has a platter that moves. It makes one complete revolution in 0.00833 seconds. Well, that's t. This is t. So what is the frequency in hertz? Well, the frequency in hertz is always the reciprocal of the period in seconds. Always. So all we have to do is take 1 divided by 0.00833 seconds. And we're going to have units of per second. I'll explain what that means in a second. No pun intended. So we're going to take 1 divided by 0.00833, and you get 120. So the answer is 120 per second. 120 what? 120 revs per second, but we write 120 hertz. Now, sometimes you were asked how many revs per minute, and you just use common sense here. I don't think you need a ratio. If it goes around 120 times in a second, if we multiply that by 60, because there's 60 minutes, there's 60 seconds in a minute, 120 times 60, I believe is 7,200. Can I get somebody to confirm it's 7,200? Thank you. So with this hard disk drive, you're talking about 7,200 RPM. Of course, with a solid state drive, you don't actually have any moving parts. It's flash memory. Number 2. So compare the frequency, and I have a feeling I'm going to have to get rid of these. If you take a 33 1/3 RPM record, I know that this is very foreign to some of you, but I hope you were aware. I hope it hasn't been lost in history that there were these things called record albums, and you put them on what's called a turntable. There was a little needle that scratched the plastic, picking up sounds. It's pretty interesting how it works. But these albums moved at 33.3 repeating. Revs per minute. Okay, so we already have the hard drive, the hard disk drive that wasn't it 7,200 revs per minute? I believe it was. So if we were to compare the frequency of the hard drive to the frequency of the record, we could take 7,200 and divide by 33.3 repeating and get a ratio. The hard drive is actually spinning faster, obviously. So the frequency of the hard drive is about 216 times greater. You were also asked to compare the period. Well, the period of the hard drive will be smaller than the period of the record by the same factor, which means that since the frequency of the record is so slow, the time it takes is so large. We could actually calculate both of them, but I think it's just reasonable to say that. Any questions with number 2? Right, number 3, a pebble is stuck in the tread of a tire, and the distance from the pebble to the center of the tire is 36 centimeters. It takes 0.4 seconds for the wheel to make 1 revolution, which means that's the period of revolution. What's the speed of the pebble? Well, the centripetal velocity as a magnitude is the speed, and we've already seen it's 2 pi r over t. I can't remember if there's a vector symbol on your formula sheet for that. Let me take a look. I would imagine it's absolute value, but we'll just make sure. Yeah, it's absolute value. There's no way that we could possibly get from this formula any positives or negatives because the direction is continually changing. So this is a really simple question, you guys. You have to take 2 times pi times r, 2 pi r, which is 0.36 meters. We want to work in meters, not centimeters, and divide by the period of 0.4 seconds, and you're going to get an answer. So do me a favor and calculate that for me. Seems reasonable. Just wait for a couple other people to chime in. Andrea's got it. We'll wait for a couple more. I'll go ahead and commit myself. Farhan, Sienna both have it. So 5.65 meters per second. Technically, we should go to 2 significant digits, but I really don't care if we go back and look at exactly how it's going to round. I'm going to say 5.65 meters per second. Number 4 rather, the diameter of a 45 RPM record. So there were these other records. You had to buy a little special insert that you would clip in here so that it would fit on your turntable. This is a 45 and it moves at 45 RPMs. The diameter is 18 centimeters. A small turtle is standing on the edge of the record while it's rotating. What's the speed of the turtle? Well, it's 2 pi r over t. I can't believe that images slow my program down that much. Let's just calculate it. Well, you need to know t first, though, don't you? We want to find out how many seconds for one rev, and this is 45 revs in 60 seconds. So you know what? When we cross multiply here, it's not 45 divided by 60. Another way to look at it is it's 60 seconds for 45 revs. We want to find out what length of time it is for one rev. I had my ratio upside down when I wrote the second part of it. So when I cross multiply here, I get 45x equals 60. So x is actually equal to 1 point. Can you help me out here? Is it 1.3 repeating? And the 3 goes on? Okay, good. Thank you, Andrea. So 1.3 repeating seconds. 0.75 was the number of revs per second, which is the frequency, which I don't care about. So now we're just going to do the calculation. 2 pi times 0.18 over the 1.3 repeating. .85. Thank you. So you get 0.85 seconds. Oh man, meters per second. 0.85 meters per second. I would like you now to do the calculation again for part B. What happens is the turtle now, for some reason, I don't know, I can't move the turtle. Maybe I can ungroup. The turtle now has made its way closer to the center of the record, and the distance is now 9 centimeters. So for question B, the radius is 9 centimeters. I would like you to calculate the speed now. So it's going to be 2 times pi times 9 divided by 1.3 repeating. And let me know if you get 0.42 meters per second. You do? Oh man, really? So I'm going to change the question here. What a drag. I'm going to change the question to radius. I should have read that better. So cross out the word diameter and show radius. Thank you, Arden and Farhan. If you do get a question that says diameter, you obviously have to divide that number by 2. So this question, I'm just changing it so it says radius instead of diameter. Do you get 0.42? You do. Okay. The speed of an object moving in a circle is greater when it's further out. I don't know if you ever did this, but as a child we would fool around on merry-go-rounds and we'd get somebody to spin it very fast, and if you stood in the center, you would move in this really slow, lazy circle. But as you started to walk outwards from the center further and further, it got tougher and tougher to hang on because you were moving faster. I'm going to end it there because, quite frankly, I think you should be able to do number 4. I'll just quickly show you. You're going to use the formula. I guess we can do it. It'll only take a minute. You're going to use the formula 2 pi r over t. And this time you know the speed. So this ancient hunter is got a rock in a sling that's being rotated in a circle at 12 meters per second. And that's equal to 2 times pi times the radius of the circle, which is the length of the sling, 1.2, divided by t. So let's calculate t. When you cross multiply, you're going to end up with t as being equal to 2 times pi times 1.2 over 12. I want to say 0.628. So you get 0.628 here. That's the period in seconds. If you want the frequency, take the reciprocal of the period. That's all you have to do here to find the frequency. The reciprocal of the period is going to be approximately 1.3, maybe 1.4. We'll find out. So there's the period. 1 divided by it gives you 1.6 hertz. Any questions with number 4? Okay, I'm sorry I dropped the ball here on question 3. I shouldn't have made that mistake. So you have to watch out for that. In some of the questions that you are being assigned, it probably says diameter. And the diameter, of course, is the distance across the center, through the center. That's the diameter. The radius, of course, is half of that. So really, all of these questions should have been done with half of that 18 to begin with. So we should have been using 9 here and 4.5 down here. But just to save time, I just said, let's imagine it's a really big 45 record. There's an assignment here dealing with basically using these formulas. T equals the reciprocal of frequency, and V centripetal equals 2 pi r over T. You certainly do not have to do the textbook questions. Okay?